Okay, so we've spent quite a bit of time talking about reactor design equations, but not so much talking about the actual rates themselves, which is still a pretty important topic in chemical engineering kinetics. So today's goal is to combine the rate laws with the design equations. So we've talked a lot about the design equations, but not a lot about rate laws. So let's look at that briefly. Suppose you have a general reaction that looks like this. So you have A and B, two species reacting to make C and D. And we'll just leave the stoichiometry as pretty general. We'll just say that these coefficients right in front are A, B, C, and D. They could be any, I guess, positive number greater than 1. Okay, as long as matter is conserved, of course. So one potential way to describe the rate is to say that the rate of the consumption of A is going to be equal to the forward reaction minus the reverse reaction. So this term over here on the left is the forward reaction. It's the rate constant times the concentration of the species A and the species B. And over here, this is the reverse reaction. That's why we have this K sub negative A. That is the rate constant for the reaction in the reverse direction, and that is going to depend on the concentrations of C and D. You'll see up here in the exponent, or the order, is the coefficients. So this is only true for an elementary, or what is called an elementary reaction. So again, an elementary reversible reaction looks like this. Why is it elementary? Well, because you have the concentrations of the reactants in the forward rate law and the concentration of the products in the backward reaction, and they are raised to the powers that are the coefficients here. Again, only true for an elementary reaction. And this is reversible because, again, we have the forward reaction minus the backward reaction. And a side note here, the rate constant is also important. It must be defined in terms to a reference, and the reference we're using here is A. So the reference just means that it needs to be in terms of one of these species here. It plays a pretty important role later on in this course, but for now we don't have to worry about it. So we're not going to worry about it. So we could express this elementary reaction, reversible rate law, in a different kind of way, and that's if we use, in general chemistry, you might remember the equilibrium constant. So this equilibrium constant is going to be equal to the forward rate constant over the reverse rate constant. So if we take this and we substitute it into here, what we get is this down here, and we can pull out a forward rate constant. So your general elementary reversible reaction can also be written in this form. Okay, so even this is a little bit much for right now. So let's say the equilibrium constant is large. What that means is that you have a very large number here in the denominator of this term, which means that it could be approximated as saying the second term over here goes to 0. Now you'll see what you're probably more used to seeing at this point in the course. The rate is simply going to be K, Ca to the A, Cb to the B. So this is the rate law that corresponds to an elementary reaction that is irreversible. So again, irreversible means that the equilibrium constant is large, so we're only going to consider the forward rate. The forward rate is going to simply be the rate constant in the forward direction times the concentration of each of these species raised to their respective powers. Now, the interesting part is that... why is this... Hold on, give me a sec. Okay, the interesting part is that this isn't the only way we have to describe a rate law. So this is an assumption that something is going to be so-called elementary. If something isn't elementary, it could even follow a reaction rate law that looks like this. Let me try to move this up so that we could see everything at once. So this rate law is another way to describe the exact same reaction that we have going on here, and it is what we call a power law expression. So this is non-elementary because, again, these exponents aren't the coefficients that are in this, I guess, chemical equation here. They are N, M, W, and Z, which are not, they might be these, but they are not necessarily these. And the reason it's called a power law is because you're simply expressing this as the product of the concentrations raised to their powers. So here we have some influence of the product concentrations on the overall rate law. And this isn't even the last way you could represent the rate. Another way is as a quotient. So maybe you have something like this, and this isn't the only quotient you could write. You could write many different quotients that will describe this reaction. This is just one I'm giving an example. So this is again a non-elementary reaction with a quotient as the rate law. So what I'm trying to get here is that there's many different ways you could propose a rate law, but it's a matter of which one actually fits the empirical data when you get down to it. So I'm just saying for now, we're not going to worry about it so much. We're going to simply say, okay, let's call everything elementary and irreversible. Back in the next chapter, we'll actually figure out how to propose a rate law and then see if it fits the empirical data that we're getting from the lab. So for now, all the reactions that we're going to cover in this lecture, we're just going to say, okay, assume it's an elementary reaction that's irreversible. So let's see what's an example of a problem that we could be given. It could look like this. So we have an elementary irreversible reaction. That's going to be this. We could specify that A and B are both going to be liquid. That's going to be important. You'll see in a bit. And we could specify the reactor that it's being run in. So it's being run in a batch reactor. And you're told to get, well, an equation that describes the relationship between the conversion and the time. So how would you go about solving this problem? Well, I'm going to tell you. The first thing that you're going to do is you're going to list all of the assumptions that go into the problem. And half of these are going to come from the problem statement. The one that we need to assume right now is that the reaction and the reactor are going to be both isobaric and isothermal. This simplifies our treatment of the reactor. You'll see in a bit. For now, take this on a grain of salt, but we'll visit this assumption again in a little bit. The second assumption that we're going to need to make is that because it's a liquid phase reaction, you notice here we're actually getting more moles of things in the products here. So if we have, say, 5 moles in the reactants, we're getting 10 moles in the product. And usually, if you had a gas phase reaction, that would result in a larger volume. But because it's liquid phase here, we're saying that the volume overall is going to be in general constant. So we could say the initial volume is going to be same as the final volume of the reaction. And lastly, just what we were saying before, we're going to say let's treat the reaction as if it's elementary and irreversible. That's going to allow us to propose the rate law. So now that we have these assumptions, the next thing we do is propose a rate law. Well, we're going to assume it's elementary and irreversible, so we're simply going to say the rate is going to depend on the reactant concentration raised to its stoichiometric coefficient. In this case, it's going to be 1. So the rate law is going to be very simple. The consumption of A can be written as the rate constant in the forward direction times the concentration of A raised to its stoichiometric coefficient, which is 1. So this will be our rate law. The next part sort of goes back to what you've seen in general chemistry. So we're going to set up a stoichiometric table, or an ICE table, as you might have heard, and we're going to try to express the concentrations in the rate law, so it's going to be Ca, as a function of conversion. Okay, so this is how we're going to do it. Say we have 2 things that are in our chemical equation, A and B. First, we're going to say, what do we initially have? And in general, this is usually be a bit more specified, but for now, I want to keep everything as general as possible. So say we initially have Na0 moles of A. Notice that because we're using a batch reactor, we're using N instead of F, because, again, it's a batch reactor. We don't have anything coming in per unit time, we just have moles. The next thing we need to look at is the change. So we're going to say, as the reaction goes, we're going to have a conversion of A. We don't know what this value of X is, but typically that's going to be given in the problem, say 0.5. So you're going to say half of the A is going to react. That would be Na0 times 0.5. And over here, because of the stoichiometry, remember, as 1 mole of A is consumed, 2 moles of B are generated. So you have this coefficient of 2 over here, and this is positive because it's a product, and this is negative because it's a reactant. Lastly, we're going to have at the end. Oh yeah, and over here, this dash means we're assuming that there's no B initially in the system. So at the end, we're going to say, okay, we're simply going to have Na0 minus Na0x. So we can just pull that Na0 out and describe it like this. And over here, we're just simply going to have 2 Na0 x. Okay, the next part is we have n's here, but in our rate law, we have concentrations. So we need to convert from concentration, well, we need to convert from moles to concentration. The way we do that, we have moles over volume. We're going to have units of concentration. So n sub a, the reason why we did this stoichiometric table is that n sub a is going to be this here. So this will be equal to n a. And we're saying that the volume at the end of the reaction, V, is going to be equal to V0, the volume at the beginning, and the reason for that is because it's a liquid phase reaction. So if we make both those substitutions, that V will be the same as V0, and Na is going to come from our stoichiometric table. We're simply going to get this as our outcome. Notice we don't need to care about the concentration of B because it is not found in our rate law, so I'm just going to completely ignore that. So now that we have both the concentration of A described in terms of conversion and we have the rate law, the last thing we need to do is combine these with our design equation. So again, we're using a batch reactor. So we're going to start with the batch reactor design equation. The next thing we're going to do is with this negative R sub A over here, this consumption of A, we're just going to sub in the proposed rate law that we had, which was just irreversible and elementary, so that Ka, Ca is going to appear down here. The next thing we're going to do is we're going to sub in what we proposed from the stoichiometric table, that C sub A is going to be equal to this. So if we put that down in the denominator, you'll see that we're actually getting a mess over here. But we could simplify it quite a bit. And now you'll see that we could then separate and solve. So what that means is that we move the dt over to the left-hand side, and the right-hand side is simply going to be everything expressed in terms of conversion. Remember that V equals V0, so we could cross those out on both sides of here and say that it's going to be equal to 1 over here, and then we could just solve like that. So then we'll actually have an expression for the conversion as a function of time. The only thing we need to know is the rate constant, which is generally given, and you need to specify either a time or a conversion, and you could solve for the other variable. Okay, let's try another one, and this time you should give it a shot. So here's your scenario. You have an irreversible liquid phase reaction. It follows this chemical equation. You want to get an expression or an equation for volume of the reactor as a function of conversion. The only other thing I'd say is there's some initial concentration of B, say it's non-zero, doesn't matter exactly what it is. Alright, so take time and try to solve it. Okay, I'm going to assume you tried to solve it, so let's take a look. Step 1, once again, is that we write out our assumptions. It's going to be the same assumptions as last time, that the reactor is isobaric and isothermal. It's a liquid phase reaction, so there's no change in volume. And we're going to say that the rate law is elementary and irreversible. Since it's elementary and irreversible, we could say that it's simply going to be, well, the rate of consumption of A is going to be equal to the forward rate constant times the concentration of each of the reactants raised to their stoichiometric coefficient. So here, C sub A is going to be raised to the 1, and C sub B is going to be raised to the second power. Here, just for the hell of it, this isn't necessary, but I want to make a comment about what the unit analysis is going to look like over here. So the rate is always going to be in concentration per time. So if you put in concentration squared over here, you can solve for K sub A. So these are the units of K sub A. Might not seem interesting right now, but I'm going to bring it up later. So, okay, so step 3. What is the stoichiometric table going to look like? This is a little trickier than last time, but it's really pretty much the same thing. So our rate law this time has C sub A and C sub B, so those are the concentrations that we'll be interested in solving for. Notice this time our table is in terms of F, not N. The reason is because we're using a CSTR, that is a continuous reactor, so we need molar flow rates, not just moles. I said to assume that there is an initial concentration of B, so we have an initial rate of B coming into the system. Okay, let's describe what this theta thing is about, because this is a little different. So theta is described as the ratio of F, the initial molar flow rate of B over the initial molar flow rate of A. And the reason we want to do that is it pretty much allows us to write the concentration, the flow rate out of the vessel in the same way that we wrote it for A. So just as we have FA naught times some quantity expressed in conversion, we have the same thing going on here, where we have FA naught times some quantity conversion. And the way we did that is we simply said, okay, call this FA naught theta B, so they could pull the FA naught out over here. The other thing to notice here is that there's a 2 over here. The reason is because the stoichiometry says that as you consume 1 mole of A, you need to consume 2 moles of B. It's also negative because it's reactant. Over here, these are put as dashes simply because we don't really care what those concentrations turn out to be. It's not that they're 0, it's simply that they don't appear in our rate law, so we don't care what they actually are. It's going to be a waste of time if we actually try to compute them. Okay, so the next step is to, again, describe the concentrations of each of these, because remember, this isn't a F over here, this is a C. So we need to convert between molar flow rate and concentration for each of these. Okay, and notice over here, what is this small v? Well, large V is volume, and small v is volumetric flow rate. The reason we need that is for the units to work out. Since this is in moles per time, this needs to be in volume per time, so the time cancels out in the numerator and the denominator, so that your final units are in concentration or moles per volume. So again, we're just going to say the volumetric flow rate at the beginning is the same as the volumetric flow rate at the end, because it's a liquid phase reaction. We don't have to worry about expansion or compression. And we could say that FA is simply going to be what's given in the table over here. Similarly, FB is what's going to be given in the table over here. So that will be equal to this. Oh. Okay. Hopefully everything has made sense so far. I know if you're trying this problem yourself, this is probably something you didn't do, and this is probably something you didn't do, but it's good to give it a try yourself first, because then you're like, oh, okay, that's why that matters, that's why that's important. Step 4. Now we actually combine everything with the design equation. So the design equation for a CSTR looks like this. The next thing we need to do is we need to sub in the proposed rate law into the design equation. So again, that rate law comes from over here. We assume that is simply going to be elementary and irreversible. The next thing we need to do is we need to sub in the concentration expressions we have from the stoichiometric table, which is going to make this look like kind of a mess. Generally always does. That's supposed to say table. I don't know what it says tab. Probably cut that off. But yeah, that's just directly from the stoichiometric table. I sub those in. And then the last thing we pretty much do is do a little bit of cleaning. So pull out all the constants and simplify like this. You're probably thinking, okay, how do these units actually work out? Yeah, volumetric flow to the third over molar flow rate squared. Well, that's pretty weird. Remember that theta is unitless, conversion is unitless. The only unit we have to worry about is this rate constant over here, which we found out earlier to be this. And over here, we have volumetric flow rate, which is in liters per time cubed, and we have molar flow rate. That's upside down, so it's going to be moles per time squared, and you'll actually see that it does come out to liters. So everything works out because of the units of this rate constant that we get from the rate law. Okay, the last problem you should try on your own is this. So again, an elementary irreversible liquid phase reaction, this time carried out in a PFR, so that's a little different. Reaction stoichiometry is a little different, but give it a try. So pause the video and give it a try. Okay, assuming you tried it, we have the same assumptions that we had last time. Technically, this should be volumetric flow rate is equal to the volumetric flow rate that's coming in. The next thing you care about is the proposed rate law. Again, you have to raise this to the 1/2 or just take the square root. If it's elementary and irreversible. Next thing that's important is the stoichiometric table, which looks pretty similar to the last one, except there's a 1/2 out here instead. Then we need an expression for the concentrations. It's also going to look pretty similar to last time because there's a 1/2 over here. And now, step 4, we combine everything. First, start with the design equation for PFR. Next, sub in the rate law that you came up with from step 2. Next, combine the rate law with the stoichiometric table. See, it's already looking pretty bad. Next, simplify out all the constants. And at this point, you should use whatever you learned from either numerical analysis or a numerical methods course or maybe Mathematica or MATLAB to pretty much solve this integral. I guess you could do it analytically if you hate yourself, but the rest of us, I would rather just use an equation solver and you'd get a final function for the conversion in terms of, well, the inputs to the system. Well, you get volume, a relationship between volume conversion given the stoichiometry that's present and the rate law that you proposed. Alright, next time we'll talk about actually proving if an elementary irreversible rate law is good, or if we should use a different model to examine our system.